This is Andrei Kolmogorov. And how many people, let me see a show of hands, how many people think that he has a theorem relevant to deep networks? Okay, so some set of you are wrong. and you will get some answers pretty soon. Well, this puzzle will be resolved by the end of these 2 lectures. We will see this guy come back. By the way, he's still working. There's a pencil in his hand. So he's ready to prove more theorems. He didn't stop. He still has a lot of influence. Okay, so thanks for the invitation. So I don't want to make a big philosophical debate in this about what deep learning theory is. I'll just give a couple philosophical points. The reason I don't want to give a lot of philosophy isn't because I'm scared of answering these questions, because oftentimes whenever there's some sort of deep learning theory panel, people always just get kind of complicated responses. So if you're curious about the philosophy about this, we can talk about it afterwards, but I'd rather just stick to more technical stuff. But I'll just give you some basics. So as everybody knows, deep learning is a practical field. It is motivated by the fact that deep learning works. It works very well. It solves lots of problems, in prediction problems that we had trouble with before. So it's fueled by the practical success. And in particular, it is not being fueled by the theory. So the deep learning theory that people are doing, me and many other people, we try to make it practically relevant. I personally run lots of experiments. I run lots of code. I check the quantities that appear in my bounds. I care whether the bounds are actually relevant to what happens in my laptop and my GPUs and stuff. And one interesting thing about deep learning theory is that there are many classical questions in statistics and machine learning that are being revisited in deep learning, and they're interesting if you go back to them without deep learning. So just 2 quick examples. One is if you just open a standard textbook, something called generalization, you find something called VC theory. You can also find the theorem saying VC theory is tight. All of that's irrelevant. And it's also irrelevant outside of deep learning. And another comment I'll say is that even basic definitions like what does generalization mean have been revisited thanks to deep learning, and they're relevant outside of deep learning. So concretely, if you look in a standard machine learning textbook, when it says generalizes, it means you trained well on your training set, and you do well on your test set. Your test set is drawn IID from the same distribution as your training set. But in reality, people care about things like self-driving cars that might run into a different type of snow than they did what they were trained on. They still want it to do well. So some people are actually bending the definition of generalization. And once again, this is interesting outside of deep networks. So there are a lot of reasons I find deep learning interesting, and I even find it interesting for this sort of reverse thing of the flow that it has back outside of deep learning. Okay, so that was motivation for deep learning to a great extent. So what is the point of deep learning theory? So for some people, the goal is to contribute to algorithms. And I can give some anecdotes throughout the lectures, but for the most part, it has been practitioners who've been creating the algorithms and the architectures and all this stuff. Maybe theorists can contribute to things outside of classification and vision for things like reinforcement learning, but let's see. So for the most part, what I'll talk about these 2 days is that mine? Is that really mine? No, I'm offline. It actually can't be me. Does anybody know what was hooked up to that? So I'm offline and my phone is over here. That couldn't have been me. I went offline. I'm always paranoid about these sorts of things happening. Okay. Yeah, that wasn't me. Okay. That was really strange, right? Nobody knows why that happened. Okay. Anyway, let's keep going. So, okay. So we're going to mostly analyze existing methods. Now, it is very fair for you to say, if we're just analyzing methods other people come up with, then deep learning theory is useless. And, it just, many people have this attitude. And like I said, I don't want to enter a philosophical debate. I'm just telling you where we are now. This is what we have. All I'm really going to tell you is what deep learning theory is like for me. So I'm a mathematician at heart. I like thinking about things mathematically. I like writing down expressions. I like writing down algebra. I just enjoy writing out math. So for me, and I'm not trying to tell you this will make you the trillions of dollars, but for me, it's actually very, for me, 4 trillion, right? So for me, this is what deep learning is like for me. It's like this alien spaceship that just crashed crashed down on Earth, and we're just like piecing through it, and we're finding like weird chips and plates and like weird isotopes and all this weird stuff. We hit it with ions, and we play with it, and we figure out what it does. One example is that, I might mention this a little bit later, but the deep learning practitioners found over time, they slowly refined a certain random initialization, a very specific Gaussian random initialization with a specific variance that just kind of got tuned over decades. I mean, if you look at Leon Batu's papers from the 90s, he talked about this random initialization. It's been tuned and tuned and tuned. It turns out that thing has amazing mathematical properties that only in the last 5 years people have started to understand. So it's like an alien spaceship crash landed, and the mathematicians many decades later started to piece it apart. So for me, it's just fun mathematically to play with deep learning. And I like thinking about it, and I like trying to analyze it. And I know that's not the most compelling motivation, but I don't want to get into the philosophical debate. And another exciting thing for me is that it's not clear what math to use to do deep learning. You know, there are people that have physics background, there are people that have statistical physics background, there are people that have, you know, just like everything you could think of, people of all kinds of math, and it all has a little part of this story. So it's pretty exciting. It's not like you just have to know what a gradient is and what convex means, and you can know all sorts of stuff or not know all sorts of stuff and go far with this. Okay, so a couple questions that we might ask in deep learning theory are, what can we approximate with a deep network? So we have some prediction problem, like Justin was talking about ants. We have ants going around. We want to know where the ants are going to go. So that's a prediction problem. We don't want to actually run ant brains, so we just approximate what they do with a deep learning model that was fit to what happened. So this question is, can deep networks just approximate certain phenomena or certain functions? That's one question we might ask. Another question is, I use PyTorch. Wait, am I too loud? I feel like I'm too loud. I feel an echo. Does anyone think I'm too loud? I can move this down. It's easy to fix. Okay. So another one is, why does gradient descent work? Okay. I mean, on the surface, there's just no reason at all why gradient descent should work on deep networks. At least the way they're written, it's not obvious right now why it should work. Another one is, why do they do so well in a test set after doing so well on any training set you feed it? This seems to be confusing, and people write many papers about how confusing this is. And we could just list many, many more questions, like why do GANs work? You know, how do I make defenses against adversarial examples? How do I interpret deep networks? Right? Like interpreting deep networks is important too. It's 20 years from now, doctors don't exist, we go into the hospital, a deep network says, take this drug, and you want to know that it's not going to kill you. Okay, so interpreting deep networks is another very important problem, and we could just list thousands of cool theory problems we could work on. Today, we're only going to talk about these aspects. Okay, so today, we're going to talk about this approximation question, what functions can we approximate with deep networks, and what we're also, and so that's today, these two, I guess, 40 and 45-minute sections, and tomorrow 40, maybe 40 and 45 again. And then tomorrow we will talk about optimization and generalization. So I should say that for today, I know the field pretty well, so I'll be covering actually very little of my own work. But just due to my expertise, on tomorrow I'll be actually presenting maybe half my own work, which isn't ideal, but it's just what I know the best. So just a warning that tomorrow will be more biased, because that's just what I'm an expert in. And just a show of hands, just so again, today we're talking about these approximation questions, and then tomorrow this optimization and generalization. And I have too many slides. So I just want to see a show of hands for people. You know, if I have bleed over, if I have extra time, or, you know, if I want to bleed one lecture into the other. So many people would prefer that I spend more time on the approximation questions. Okay, how many people would prefer I spend more time on the optimization and generalization? Okay, seems like there's a bigger show of hands for that. Okay, so my optimization, so those slides are worse. So I'll just guarantee, was there a question? Did I hear something? So I will just guarantee that I will not bleed over this lecture. And if we're taking too long today, then I'll just, you know, cut stuff selectively throughout today. Okay, so that's the story for today, and that's as much philosophy as I want to give. I've walked around and spun around. So is that me? It really. So I don't even have Skype running on my laptop. Yeah. Yeah, Skype's not even running on my laptop. So, and my phone is here, so. Yeah, but it's plugged into the speakers. It's just weird. You know what? Is it this? No. Okay. Too much. Okay, I'm wasting too much time on this. I think it's that computer. And somebody say, answer it? I mean, I can talk over this, but it's just kind of weird. Oh, whatever, I'll just talk over it, but it's pretty strange. Okay. Yeah, whatever. I'm just gonna talk over it. Hopefully, everyone else is less distracted than I am. Okay, let's try to focus. So let me. There is actually a solution to this, by the way. So if this lasts for 20 more seconds, I'll do the brutal solution. The brutal solution is I'm going to turn off all the audio, and I'm just going to yell. That's actually a solution. No, it's not my laptop. My computer is not on the internet, and Skype is not on my computer. Oh, I see. I see. Okay. Can we just turn off the audio? I mean, this is becoming like less funny. Okay, I'm just going to keep going, all right? Because they don't want to turn off the audio. I'm just going to keep going. What was it? What was it? Wait, what was it?
It was for some reason it was calling here. This
Oh, okay. Anyway, sorry for that. Welcome back, everybody. We're talking about deep learning theory. This is Andrei Kolmogorov. That's a spaceship. Okay, no, we don't actually have that much time, and I do want to cover a lot of technical stuff. So let me cut out my own jokes a little bit, and in the 20 minutes we have, do a little bit of technical stuff. So for these approximation lectures, so let me make it into a mathematical problem now. I haven't made it a math problem yet. So the math problem is nature is going to be determining its dynamics via some function f, and I want to replace that function f with some neural network g, okay? That's our job. Nature's dynamics via some function f, I want to replace with g. And I want to argue that this goes well, okay? That I can do this in general. I should step away. So this notation won't matter too much if you haven't seen it before, but for the people that are familiar with it, I would say that the bottom line thing we want to guarantee is that if we have some notion of error or risk for our problem, so all this notation is saying is putting the integral over the x, y pairs in my, in my training distribution, my test distribution, whatever, my prediction problem, and I have some loss function L, and I want fx and y to be close. So on the left is if I was using the best, some like nature's perfect function, and on the right is if I had some replacement neural net. So I want these two quantities to be small, to be close. Okay, I want the prediction error with the true good function and the prediction error with the deep network to be similar. So I'm claiming that this is our ground truth problem that we want. Okay, that we want these to be similar. What you actually see in papers on approximation is a different question. So people say, oh, well, under some conditions, which you can read here if you're familiar with this lingo, if under some conditions, I can relax this problem and say just, I want G and F themselves to be close. So if G and F are always close, then it's also the case that they'll be good on different prediction problems. But all I'm trying to motivate here is that one exciting thing about deep learning is that we don't even know the right questions. So in deep learning, it's not just that we're trying to prove things, we don't know what to prove. And many papers, they say, oh, we're going to approximate a function, and therefore our theorem is going to be, G and F have to be close in this norm or that norm. But actually, they've already changed the problem a lot. the real problem we want is that the predictions are similar in terms of this risk. Okay. But for today, mostly what we'll see is this form of the problem here. So I want G and F to be close on average, which is written here on the right-hand side, or I want them to be close everywhere. That's this L infinity. Okay, so that's what we're talking about today. And we'll also talk a little bit about lower bounds. So we want them to be far apart, on average a lot. So it's not enough for G and F to be different on one point. We want them to be different on the prediction problems. They should be different on many points. They should be different on average. Okay, so just so this slide is clear here, many papers on approximation, they just say we want to do this or that, but what they really should be saying is that they want the errors of the two different predictors to be similar. And today we'll just be doing this metric version of the problem, which is the standard one. We'll be saying that G and F have to be close on average or everywhere. Okay, so what we'll be doing today's lecture mostly is just picking F's and then constructing G's that are close or not close. Okay, and just a little bit of terminology. When I say deep network, here's the simplest version of a deep network. Let's just unroll this from the inside out. You give me your input X, and then I form this affine mapping A1X plus B1. So A is a matrix, B is a vector. I take your vector X, I hit it with a matrix, get another vector out, apply this nonlinearity sigma, and I just keep doing this iteratively. Okay? This is just another way of writing a standard feed-forward network. Take your input, hit it with a matrix, add a bias, hit it with nonlinearities, hit it with a matrix, add a bias. You can write convolutional layers in the same way. We're just going to treat this as our formalism for today. Okay? Okay. There are many other conventions, like recurrent networks. Not really going to talk about them. And for the most part, I'm going to talk about this thing called the ReLU. The ReLU is a very simple activation and also very nice mathematically. It's just the identity function, but you zero out negative things. And I'm just giving a random citation. The Neocognitron paper from the 1980s, from actually 1979, is I think the original posted date. This paper has convolutional networks, and also the ReLU is in that paper. That's just one of the early references to a ReLU. Okay. We'll usually use that mostly because you can switch between activations very easily mathematically. And just one thing to look out for in all the constructions today. I moved it down. One of the things to look out for in the constructions is the constructions are going to be a little bit chaotic a lot of times, and this actually is an issue. So if it seems like the functions we're constructing are kind of wild and kind of have steep slopes and stuff, that actually is a problem. And it's kind of hidden in many of these theorems. So feel free to ask about that. Okay, so here, was there a question? Okay, so here's our plan for today. So let me just tell you what all these parts are. So the first part is, or actually let me start from the second part. So many people, when they say that deep networks can fit anything or they can fit any continuous function, they usually cite some textbook theorem, and if you look at the proof in that theorem, that proof cites some other textbook, and then that textbook cites some other textbook. And so I'll give a couple of these standard ones, but I'm also going to start with just some elementary constructions. This is actually the most exciting part of the talk for me. I want everyone to walk out and feel like it's very obvious that deep networks can fit anything. It's not like some mysterious thing and that uses 20 PhDs of effort to understand. So those are maybe the main parts. And then the other topics I want to cover, the first one is something I've just labeled as benefits of depth. So people, of course, in practice use deep networks, not shallow networks, and all those initial constructions will be 2 or 3 layers only. So I'll have a section where I talk about how many things can go wrong if you restrict the depth. Then I'm going to talk about approximation of another kind of approximation that benefits from depth, which is functions that are very smooth or easy to approximate. And for that, I'm going to actually be talking about a result by Dmitry Yarotsky, where I lost you somehow. Do you mind showing a hand? Where's Dmitry? Did he walk out? Oh, there you are. Okay, yeah. So that's his result. And then I'm going to finish with a bunch of kind of random comments, including why Kolmogorov is here, other than having given us a measure theoretic probability. Okay, so any questions so far? That's the basic timeline, and like I'm just going to pick and choose. I'm going to skip a bunch of slides based on what seems to be how many Skype calls we get basically. Okay, so the part this might be the only thing we can do before lunch. So I really want to go through this elementary universal approximation. To be clear, what we're going to be showing here is that shallow, actually, networks with just 2 or 3 layers, can approximate any continuous function. Okay, so continuous functions means they're very regular. Okay, they're not that wild, and I want to be able to say that there exist deep networks that can approximate any such function. And we're going to do it kind of in an elementary way. So just to warm everybody up and have some fun, let's start with some univariate stuff. And I bet a lot of you are looking at this and saying, oh, I know how to solve this problem, why am I sitting here? Well, even for this easy version of the problem, there are some cute things that start coming up. Okay, so I want to fit this with a deep network, or a shallow network actually, and that's easy enough. All I do is I just take in my x, and for now I'm just using step function activations. So I just take in my input, and then at every one of those little red offsets, I just stick a step function, and I just add them together. Okay, so the meaning of these step functions is when I change the offset, that moves the step function around, and then the coefficient changes its height. Okay, so I've rewritten the blue curve as a summation over these linear combination of these shifted step functions. So this is a one-layered, this is a neural network with one hidden layer. And already some interesting things happen here. So one thing I want to point out is that we've already done something that polynomial approximation cannot do. So polynomials are very bad at approximating flat regions, other than constants. So if you have a function which is flat for a long time and then spikes, good luck doing that with polynomials. The degree of the polynomial you need for this blows up. Okay? If you take any of the standard interpolation type theorems, they choke on these kinds of constructions. E to the x with even e to the x. So, okay, sorry, e to the x wasn't what I wanted. I want a step function, sorry. So approximating just like a step function with polynomials is a disaster. Okay, so already we've done something that is difficult with polynomials. Okay, so now let's look at a more interesting function. So I want to do a smooth function now. And so how am I going to do this? Well, you can kind of guess how this is going to go. I'm going to bunch up a bunch of step functions as the slope increases. More slope, more step functions. Okay, so I stick them like this. And you say that makes sense. If you thought about this problem before, you know some of the lingo, you can actually write down one way to do this explicitly. I say that if I want to be epsilon close, the number of these little bumps I need is going to be like the Lipschitz constant over epsilon. If you think about it, the Lipschitz constant is the maximum slope, and the slope is telling us how to convert between the domain and the range. Okay, so this is totally intuitive. But actually, even for this problem, there's a better solution. So the problem with this construction is the same as the problem with kind of the naive way of doing this, where we don't want to pay for the flat regions. So for this, if I just say the number of steps I need is equal to the Lipschitz constant over epsilon, I'm paying for the flat regions. You know, there are regions that have a big slope, and I'm paying for that big slope everywhere with this bound. So there's a better bound just by the fundamental theorem of calculus. So the slides are uploaded. You can check this calculation later. I can just rewrite the function f as an integral over step functions. Fundamental theorem of calculus. That's this entire proof. Fundamental theorem of calculus and just some playing around with the bounds on the integral. So what's happened here is I've rewritten f as actually a network with infinitely many nodes, okay, just infinitesimals, infinitesimal coefficients. And now if I look at how many of the step functions I need, it's the integral, it's more like the L1 norm of the function f. So it doesn't pay for the flat regions. So what am I telling you here? I'm telling you, first of all, that for univariate functions, you can kind of cook up the approximations very easily. And I'm also telling you that if you really just spend too much time doing it, then you find out that kind of the generic classical bounds on this are actually very loose. Okay? Okay. So let me just point out really quickly, because I don't want to spend too much time on this, that this was with the step functions, and I promised you we're working mostly with the ReLU. So if I do this, if I look at the ReLU, so whereas step functions, I need to add a step function every time the range changes a lot, ReLUs are added every time the slope changes a lot. So intuitively, they're kind of working in derivative space. And so if I do the same argument with the fundamental theorem of calculus, I get a dependence on the L1 norm of the second derivative. Okay, so what I'm saying is that the number of ReLUs I need to approximate this function scales with the second derivative, and for step functions, it scales with the first derivative. Okay? So to be clear, like, you know, this construction here, you can just do it on pencil and paper, but I'm pointing out that even for these kinds of problems, they're kind of like neat things if you go through the details. Okay, so this is univariate approximation. Now let's go through multivariate approximation. And let me just point out, just to kind of just fact so that there's no time wasted on it. So far, we've been trying to approximate functions exactly everywhere. I've been constructing shallow networks that are equal to the target function. But if I only want to approximate something on a finite set of points, okay, so I'm not approximating function everywhere, I'm just approximating it on a finite set of points, there's actually a trivial solution. The trivial solution is pick a random direction, and note that all the projections onto the random direction are distinct with probability 1. And now I can just do univariate fitting along that line. Okay, so I can take the earlier, I've reduced it to a univariate problem. All of these points have unique projection onto that line, and I can just do univariate fitting on that line. So if your goal is to make a finite point set, there's this trivial solution. It's not a perfect solution. Some of the points might map very close to each other, in which case we need a very big approximation, but still it works. Okay, I'll just leave this as a technical fact. I don't want to dwell on this one. Let me talk about a problem that we care about a lot more, which is approximating multivariate functions and multivariate objects. Okay, so far, I've been saying we want to approximate univariate things, and the constructions are very clear. You know, if I need to approximate a function that just is this step like this, you know, I can just put a step here, or something like that. I just track the changes in the function and add my little units there. But for multivariate functions, it's not so easy. Okay, so to be clear, what I'm trying to do here is I want to approximate a function which is 1 inside the box and 0 outside the box. Okay? So if we try to do what we did before, which is every time the function changes, just put a bump there, put a ReLU or a sigmoid or whatever. If we do that, watch what happens. So I just keep adding these. So I've added 4 supporting hyperplanes, and if I add them up, then I don't get the function I wanted. Okay, because the center region has 4, it intersects with 4 of these half spaces, and then there are 4 regions that have 3 intersecting half spaces, and there are 4 that have 2 intersecting half spaces. Does everybody follow what I did here? This is like a 3D plot, flattened down to 2D. I wanted a function which is 1 inside, 0 outside. I added these 4 supporting hyperplanes, added them together, and I didn't get the function I wanted. So so this is a network with 1 hidden layer. So does anybody see a trick way to adjust this construction to actually get the function we wanted, namely 1 inside and 0 outside? Yeah? Okay. So your suggestion is that we have steps that actually have corners, for instance? Yeah. So his suggestion is one of the solutions, which is, I should always repeat the answer, so because of the mic. So he was saying that we can have a different type of step. So if we actually had something that was more like a bump, for instance, a function which is a corner, then I could add them together in the appropriate way. But I'm not letting you do that. You have to work with this setup, which is you're just adding these functions that are 0 on one side of the hyperplane, or some number on one side of the hyperplane, and a different number on the other side. See, this is why I think this problem is really cool. People have these like textbook theorems they cite, but if you start thinking about how to do the problem elementarily, it's actually extremely hard. Exactly. So that is one solution. Just to be clear, so that's what we're going to do. His suggestion was we add a layer and add a threshold. But just to be clear, I think you were trying to figure out how to do it without adding a layer. Okay, so now we're going to add a layer. So I'm going to add a layer, and yeah, sorry, I realize I'm used to having a whiteboard. So I'm going to add a layer, the layer is going to say, if my input is greater than 3.5, then I'm going to say 1. If it's less than 3.5, I'm going to say 0. Okay? So we do that. We add this layer. Oh, I didn't realize this. Yeah, so the producting half spaces together is another way to get your solution. We'll come back to that. But so we add a layer and we threshold, then we get the thing we wanted. Okay, so now we've used 2 hidden layers and 3 layers of affine mappings. So that works. But to actually do it with only 1 hidden layer is weird, actually. It's actually hard. Okay. So I'm going to give you the only construction I know, the only intuitive construction I know for how to do this with 1 layer and just doing the hyperplanes. I really don't know of another one. Any other construction I know, I mean, sorry, when I say intuitive, I mean I can like see through the entire, I almost feel like I can move piles of sand around and construct it. We are going to go through other theorems that prove this, but they're all going to have a lot of technical, just like rabbit holes. So here's another idea. Instead of trying to approximate squares, I'm going to try to approximate balls. Okay? So let's try to do what we did with the square, which is we just add together all the supporting hyperplanes. So now I'm going to take just supporting hyperplanes to this circle, and I'm going to be 1 on one side, 0 on the other side. I'm just going to keep adding more and more of these together and averaging them. Before I put the slide up, just think about it. It's actually pretty weird once you start thinking about it. I'm going to add together infinitely many hyperplanes. Okay, I'm going to keep adding more and more hyperplanes. And if you think about it, what's going on is that very close to the circle, I'm actually on the plus side of many of the hyperplanes. The farther out I go, I'm on the plus side of fewer of them. So if you do this, you actually get a function which has a large value in the center and then attenuates with these like 1 over x, with these like strange tails. Okay, this is a very strange function. And I have not actually proved this, but it appears that this construction requires an exponential number of nodes to approximate. We'll come back to that point. Okay, but the point is that now we have what I would call a bump. Okay, it's a function which is positive in some local region and small in other regions. It's kind of like the function that was suggested earlier over here. Okay, so I just add together a bunch of hyperplanes to get a function which is large in some small local region and small outside of it. And now what I can do is I can just take any function and I can just write it as the sum of a bunch of these. I take a function, I look at where it's large, where it's small, and I just add together a bunch of rescalings of these bumps. And I won't go through it here because of time. If you check the slides, there's actually a trick proof that this is possible. There's a trick proof by convolving the function with the bump that very easily proves that this works. So, yeah, this is, let's see what we're doing with time. This is the last, I think, like serious technical thing I'll cover before lunch, and I realize we moved kind of bumpily because of Skype and me and all these things, my jokes, but let me just be clear on what we're doing here. So our goal was an elementary approximation of continuous functions. We noted that in 1 dimension, it's very easy. We just stick bumps, or we just stick our nodes every time that the function changes a lot or has a big change in slope. And then when we went to the multivariate case, we couldn't do that anymore. If we added a supporting hyperplane in one place, it changed the function in a lot of places, not just where we wanted. Right? That's what was bad here. I want to just increase the value of the function inside that blue square, but I have to increase it everywhere. So we run into this issue. And our solution to the issue, or one solution to the issue, is to just add together many of these things, and I get this weird bump function, which you can analyze, that has this attenuating property I say. And then to approximate general functions, I can convolve them with these, or just write them as a combination of many of these. And that gives me what I want. So we'll give maybe I can just jump to a formal theorem statement. If you use this, you get a theorem just to end on an actual theorem. You can use that to prove a theorem kind of like this. I think due to time, that's where we should probably, yeah. So this, I don't want to be the barrier to lunch. So this is one of the standard universal approximation theorems. We'll cover it in detail in its proof in a couple, I guess, after lunch. So this theorem is saying you give me your activation function. Earlier I was saying ReLU or step or whatever. Your activation function, what we need for it to do, it needs to go to 0 on one side and 1 on the other. Okay? and I also need continuity. But anyway, so we have this function, and I look at all the functions I can compute with single node neural nets, okay? H sub sigma, that's all the different functions I can get with individual nodes. If I compute span of H sigma, that's linear combinations of nodes. So that's a network with one hidden layer and two affine layers. Okay, so this class of functions, so networks with one hidden layer and this kind of activation, can approximate continuous functions on compact sets. And I've sketched for you in a very kind of intuitive way one proof of this. The one proof was by first constructing these bumps via infinitely many supporting hyperplanes and then convolving them with the function. But then after we come back from lunch, just to make the timeline clear, what we'll do after lunch, so that was the classical universal approximation theorem. We'll first give a couple different classical proofs of this. These are the standard textbook ones you see. But I just want everyone to have kind of the intuition first. And then based on time, we'll talk about cases where depth helps, because this was a shallow construction. So I'll talk about cases where depth helps. We'll talk about this approximation result by Dmitry over here. And then we'll talk about a bunch of things like our friend Kolmogorov. Okay, so I didn't take any questions because I started panicking a little bit after the late start in the Skype, but we'll be a little bit more relaxed after the break. I don't care if we skip half the slides. It'll be more interactive after the break. Okay, see you after lunch. Intuitive, or I hope intuitive descriptions of how these things could work internally. And the reason I do that is because even though all of these papers have 10 to 20,000 citations, I rarely meet anybody who can tell me the proofs and how the proofs work. It's very, very rare. So people just kind of cite them, but I wanted everybody to have an intuitive feel on how they work. Okay, so here's one of them. There were three kind of main ones that came out in that year, 89. So okay, here's the statement. It says, give me my activation function. That's the thing we applied to the affine mapping. So here's my activation function. It needs to be 0 on one end, 1 on the other. And it also needs to be continuous. Sorry for leaving that out. Okay, 0 on one end and 1 on the other. And now I define this class I'm calling capital H sub sigma, subscript sigma. So this is the function class I can represent with neural networks with a single node. I take my input, I hit it with some affine combination. So in other words, A transpose X minus B. And then I add 1, and then I apply 1 nonlinearity. So this H sigma is the set of functions I can get with single node networks. Okay, so span H sigma is the set of all possible linear combinations of H sigma. So it's all possible linear combinations of single node neural networks. So that's what you get with neural networks that have one input layer of an affine mapping, a bunch of nonlinearities, and then one final affine mapping. That's equivalent to span H sigma. So span H sigma is a network that has 2 affine layers and 1 nonlinearity. Okay, so this function class uniformly approximates. What that means is that, I'll explain that in a second, it uniformly approximates continuous functions on compact sets. What that means is you give me a continuous function and an epsilon, and I will hand you back a deep network, in this case actually a shallow network, but I'll hand you back this network, and for all x in some bounded set, it's epsilon close. So it's epsilon close to this target function. That's the theorem. Okay? So this is the standard thing that everybody means when they say universal approximation. And for many people, this is kind of the starting point of a lot of the deep learning approximation. This is what a lot of people kind of cite as the starting point. It's not the starting point, but this is kind of what many people were inspired by these results in the late 80s. Okay. So now that we've nailed that down, do we have any questions from anything in the lecture so far? Yeah? Yeah, so this function sigma, it's 0 on one side and 1 on the other. So you can consider it to be like a sigmoid or, yeah. You can do ReLU, I'll explain that in a second. So you should just believe me for now, this is basically anything you want. You can reduce other things to these. Just for technical reasons that it's this way. Okay, no questions? Oh yeah, so this result is very finite dimensional and can be false in infinite dimensions. Yeah, it's very finite dimensional, yeah. Yeah. Let me just say one more thing that makes it clear to you, because I'm also over compact sets. In infinite dimensions, compact sets have a very different meaning, and it breaks kind of bounded rather, yeah? We don't require this thing to be monotone. So let me explain the question in a little bit more words. So he was asking if sigma can be monotone, and what's going on in this construction is that I'm saying it's 0 on one side, 1 on the other. And I'm allowing it to be really wild in the middle. But what we can do is I can just multiply the inside of what's inside of sigma by a large positive constant, and then squeeze that wild part into a smaller and smaller region. So I can kind of make it less relevant. Okay. Oh, that's actually so the question is, why is it A transpose X minus B? Incidentally, all of these conventions are non-standard. If you look at the PyTorch documentation for what a linear layer does, it actually writes X and then A transpose. And A is a matrix. It reorders everything. So all these things are just conventions. The reason I did minus is because kind of in my head or in my heart, because this thing is, I'm not sure which, because this is 0 on one side and 1 on the other, I think of it as a step function. And so by making it minus b, I'm kind of putting an offset somewhere. So if 1 was actually the indicator function, which it isn't because I said this is continuous, but if it were the indicator function, A transpose X minus b would be, if it was just X minus b, it'd be something which is offset, and the step appears at the position b. So it's just an intuition of it as a threshold that's been moved. Not a stupid question at all. And in fact, I think in the original slides, I wrote A transpose X plus B, and I switched it here. Yeah?
So in principle, would it be necessary to try to infinite amount of these non-linearities combined together to get this uniform?
Yeah, so the question is that this thing span, so the mathematical definition of span, linear combination, is actually a finite combination, so a network with finitely many nodes. But we can ask about having infinitely many. Actually, technically, that's what this theorem talks about, because if you look up the version in the books, it has a closure, which is kind of like taking having infinitely many. For many functions, if you have infinitely many nodes, you can represent them exactly. Let me just make a side comment about this. So many of the constructions that people prove here classically have infinite width networks. They have a network with infinitely many nodes, and then you use some sort of sparsification trick. You just kind of wipe away the nodes that don't matter. And that's what people did a lot in the 80s and before, but actually recently many people, for modern analysis of deep networks, I'll talk about this tomorrow's lecture, people actually use infinite width networks a lot again. So it's a very convenient formalism. Okay, so let's maybe move on. Let me explain a little bit about the proof, just so we can have a little bit more intuition. So I'll actually go backwards in the slides here. So this particular proof and this particular theorem, it's based on, I would say, one key concept, which is that for representing multivariate functions, having the ability to multiply things together is beneficial. Okay? So again, I'm saying that multiplying helps. So deep networks or neural networks don't seem to have the ability to multiply easily. We take our input, we form an affine combination, and we just keep adding together nodes. We're always adding nodes, whatever, multiplying nodes together. So why is multiplication good? Well, another thing I did in the first half of the lecture is I said, if we build all these supporting hyperplanes, we can build bumps, and once we have bumps, we can move around and add together bumps and approximate any function we want. So bumps are good, and one way to get a bump is just to multiply any sort of reasonable function, or if I have some function which has a little bit of a bump, I can multiply them together and squeeze it. So let's look at this little plot here. What I've done here is I've taken cosine x, and cosine x, we can just approximate that in a univariate fashion like we did before. If I multiply cosine x with itself, it becomes a narrower and narrower bump. If you're imagining if I want to approximate some function that has a lot of sharp oscillations, I can just add together a bunch of these exponentiated bumps. That's one way to do it. Okay, that's univariate. We were saying earlier that univariate's easy. So for multivariate, here's two ways that we can use multiplication to kind of get these multivariate bumps. So the first thing is just the indicator on the box that we were talking about, and that's the indicator of, that's the product of indicators on univariate boxes, or yeah, coordinate-wise boxes. Also, I could just product together a bunch of these cosines. So all I'm saying here is that if we had the ability to multiply, then we could find these multivariate localized bumps. If we have little localized bumps, we can just add them together and approximate anything we want. Okay, so if we add multiplication, we can approximate anything we want. And then I point out a funny trig identity to you, which is that there is a way to write down product of cosines as sum of cosines. Okay, this is just a standard trig identity or an application of a standard trig identity. So product of cosines can be written as sum of cosines. What that means is that if I write down a neural network with cosine activations and I product together a couple nodes of this network, I can actually rewrite it as a sum of nodes. Okay, so I can write it as a linear combination of nodes. I can write it as a neural network. Okay, so there actually is a way to take a network with products and write it without products. So I should say that this was interesting to me many years ago because there were people that there used to be a lot of papers on things called sum product networks. There's still papers on it, just fewer. But the sum product networks, or neural network architecture with explicit multiplications. And slowly it seems to have fallen a little bit out of fashion. I won't say definitively what the community thinks, I don't really know, but it seems to have fallen out of fashion. And perhaps one reason is we can always just rewrite these multiplications in other ways. Okay. So multiplication seems to be good. And that is how this theorem I was mentioning is proved, this particular proof. So one of the classical approximation theorems from 1885, Weierstrass, says that polynomials can uniformly approximate continuous functions. And I won't read most of this. One of the things about this is that there are many proofs of this theorem, and they're pretty cool. So if the theorem sounds interesting to you, I urge you to look at many proofs, including Weierstrass's original proof. I will just say that there's an extension which says that not only can polynomials approximate continuous functions, things that look like polynomials approximate continuous functions. So what I mean by looks like polynomials, one of the properties of polynomials is I can take two polynomials, multiply them together, I get another polynomial. I can also take polynomials, add them together, still get a polynomial. So the Stone-Weierstrass theorem says that things that look like polynomials in this way, they also can approximate continuous functions, and that's how this thing is proved. You can prove that just like polynomials, you can multiply neural networks together and stay within the same class of networks because of this trig identity, and that's one way to prove this theorem. So if you're curious, you can look this up. The slides will be online, and here are basically, if you believe this theorem, this Stone-Weierstrass theorem, then here are two essentially one-line proofs that invoke that thing to prove this theorem. Okay, so if you're curious, you want to see the slides, basically one-line proofs of this theorem. Okay, so a few comments about this theorem. So there was this question about the ReLU, and the ReLU is actually completely fine. What I can do is instead of having a ReLU, I can have an activation which is 0, then just a little bit of a piecewise affine slope up to 1, and then it's flat at 1. So I invoke the theorem as a lemma with that activation, and then I take those things and I rewrite them as two ReLUs. So I just duplicate them with the minus sign, and then I'm done. So this thing works for ReLUs and all sorts of other stuff. I should say that this is a good question. So I've seen papers that they say that these classical theorems don't work for ReLU. They totally work for ReLU. Okay. Let me also say that this construction is very impractical. It's exponential in dimension. This thing is absolutely huge. If you try to work out under the hood how big the construction is, it's just completely massive. So this theorem is not saying anything about, there are a number of reasons why this theorem is saying nothing about what happens in practice. One reason is that we're not controlling for any of the weights, so the weights might be very large and just very wild. They're never going to be found by gradient descent. Also, it's exponential in dimension, and of course, for people that download all the PyTorch, whatever, CFAR's input dimension is 3072. So you don't want 3072 in your exponent. Okay. So let me check on the time. Okay. So let me just say briefly, again, these slides are posted. There are many of these theorems, and I've looked through I've looked through a lot of the proofs, and even though I would just say that these theorems are kind of not really relevant to what gradient descent is doing, they still say interesting things about what's possible with deep networks. So just kind of picking out one of these at random, I'm just staring at this Barron one. So Barron from 1993, the way his proof works is he effectively constructs an infinite width neural network to approximate continuous functions via a inverse Fourier transform. And this inverse Fourier transform gives the coefficients on the network. Okay, it's like completely beautiful and kind of awesome. So if any of this sounds interesting to you, I urge you to look at these papers or ask me later. I won't go through them in detail. But here are the takeaways I want everybody to have, the main takeaways from this part of the whatever lectures tutorial. So again, we were saying that the classical main theorem people say for approximation power of deep networks or shallow networks is this universal approximation, which means that we can get as close as we want on these bounded sets. And I kind of sketched for you this elementary proof where we took circles and a bunch of supporting hyperplanes. I mentioned to you this proof that uses polynomials. This is one of the standard ones people cite all the time. And I also said that the size estimate is very bad. So the network we get out of this is impractical. If you take CFAR, it has dimension 3072. It's not going to be good. So in particular, there are a couple huge weaknesses with everything I've told you so far. So one is everything was a shallow construction, so it gave no evidence why we should do deeper networks. Right? We can fit continuous functions with this, so why should we add layers? And even worse, if you study the proofs really closely, you'll realize that the proofs actually work for basically every other machine learning method. So the same proofs say that boosting of shallow decision trees is a universal approximator, that RBFSVM is a universal approximator. You can actually use the same proof. So when I was teaching this stuff some years back, I'm not going to teach it anymore probably, but when I taught it some years back, I actually used the same meta lemma to prove all sorts of machine learning methods are all universal approximators. So this theorem doesn't actually really tell us that neural networks are that nice. So if you've been feeling that criticism, one person came up to me after the first half, you've been feeling like, wait, is this really about deep networks? You were on the money the whole time. You were on the $4 trillion. Okay. So any questions before I move on? Okay, yeah? They should have been posted. Where's Oh, Rodrigo, is there any way the slides can be posted at some point? Or? Yes, and my next slides will be done 1 minute before the next lecture, so you can find it then. Okay. Okay, so let me just double check how we're doing on time, because I'll keep my promise about doing all the optimization and generalization purely on the next lecture. Okay, so I want to tell you a little bit about something which is known about why adding depth to the network helps. And I should say that this is still extremely incomplete, and also none of the theorems in this section will say why gradient descent on deep networks helps a lot. Okay, so we actually don't have any optimization guarantees that, well, there's kind of one, but we don't have any very compelling optimization guarantees for deep networks yet. And that's definitely not something I'm going to cover, even try to cover in this section. Okay. So let me just give you a couple, you can come back to that slide later if you want. Let me give you a couple interesting things that happen with depth. So I constructed this function, this radial function. If you remember, I took circle, indicator on circles, all the supporting hyperplanes, and I claimed it attenuated, blah, 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 blah. And I also hinted that this function is actually hard to represent. It needs lots of these hyperplanes, a lot of these supporting hyperplanes. So here's the one concrete thing you can prove. You can say that there exists a radial function f. So just to be clear, what I mean by radial is that I take my input, and then I hit it with a norm, an L2 norm, and then I apply some univariate function to that. Okay, that's what I mean by radial function. Okay, so there exists a radial function, f, that can be written with 2 ReLU layers. So 3 affine mappings and 2 ReLU layers, and it has polynomial width. Okay, so it's a pretty small network. It's polynomial width, polynomial in dimension. And there exists some probability measure so that if I look at the distance between these 2 functions, so let me say more clearly. So I have my function, that's this radial function written with 2 ReLU layers. If you give me any other function that is written with 1 ReLU layer, even if it has exponentially many nodes, it's going to be at least a constant away from this original radial function. Okay, so once again, just saying it a little bit more briefly, I have some function f written as a three affine layer network, or two ReLU layer network, and it's at least a constant away from any sub-exponentially sized single ReLU layer network. Okay, so by another way to say it is that adding one layer, I get to cut down on the width by an exponential amount. Okay? So again, the point of this is saying that depth is helping a little bit. Sorry? Oh, omega is just a notation for saying that it's lower bounded by some constant. And the key thing here is that constant is independent of dimension. It's a universal constant. So probably like, I don't know, 10 to the minus 100 or something to be safe. Okay, so yeah, this is saying that if nature is modeling things with this two ReLU layer network F, then you really better be using two layers, or else you have to have an exponential width. Okay, there's a similar result in the literature. Let me actually skip this to just a refinement of the same one. And let me actually skip the intuition on the proof. So let me give one more construction in this part of the talk. So far we've said that if we have two ReLU layers, then we can kind of do exponentially better than one ReLU layer. Okay, so adding one ReLU layer on top of one layer kind of exponentially helped us. But now a natural question is, what about 3 to 4? Okay, ResNet, people often use like 50-layer ResNet, 100-layer ResNet. Okay, it's not just 2 to 3. The question is big numbers versus big numbers. Okay, so we only actually have one result of this type. So I'll go through the proof of that. And first for the intuition, so let me just give you an intuition on why depth could possibly help a deep network. So for the first part of the talk, I was saying that we can approximate functions if we can approximate bumps. So in other words, if I have some function with some shape, just kind of every time the amplitude or the height of that function increases, I just stick another bump there. Okay, so I can approximate functions with combinations of bumps, but it seems like I need as many bumps, I need to add together as many bumps as there are in the function. Okay, so if the function has 10 spikes, I need to have 10 nodes in my network, or order 10 nodes in the network. Okay, so what I'm saying here is that intuitively, shallow functions, they have to work a lot to capture kind of oscillatory behavior, whereas maybe deep networks can do something else. Okay? So let's go through a construction for that. So here's a very easy function. It was actually studied in dynamical systems. So if you Google this, you can find all these dynamical systems papers going back to the 50s called the tent map. And all this function does is it goes from 0 to 1 with a slope of 2. So the domain goes from 0 to half, the range goes from 0 to 1 with slope of 2, and then slope minus 2. Okay, so this little tent map function. And I've also written it as a difference of two ReLUs. Okay, so this is something you can write with a one-layer neural network, no problem. Okay, difference of two ReLUs. Okay, so here's the cool thing. So if you take this function and compose it with itself, okay, so this thing has one bump. Can anyone just guess what happens if I compose it with itself? How many bumps do I get? I think I heard the right answer. Yeah, 2. What if I do it one more time? So now compose 3 of them together. 4, and then 8. Yeah, so it goes exponentially. Okay, so this is pretty exciting. So earlier I was saying that if the target function had some number of spikes, I needed roughly that number of ReLU nodes. But now if I'm doing composition, I'm increasing the number of compositions linearly, and I'm increasing the number of bumps exponentially. Okay, so I can get a function with exponentially many oscillations with a linear amount of work. Okay, so this function is really cool, and this function kind of intuitively, at least so far, captures the power of composition. Composition lets me find at least some function. I'm not claiming that this is the most important function in the universe, but it lets us find some function which is very hard if we could not compose things together. Okay. So let me give a brief theorem. This is something I did 4 years ago. So let me actually just say it in words before I write the math up. So the earlier theorem said there exists a two ReLU layer function that if you try to approximate it with one ReLU layer, you pay exponentially as much. So the theorems were not satisfactory because they went from 2 layers to 1 layer, and we want to know about ResNet 100 versus ResNet 50 or something like that. So here's another theorem. It's not going to be, I would say, the ideal theorem. The ideal theorem would be you come to me, you say 50 layers is the best thing ever, and I would come to you and say, no, 51 layers is the best thing ever. So here's how this theorem is going to work. You're going to come to me and you're going to say, I believe in networks with, let's say, depth 100. Okay, we'll just call it k. It's going to be a free parameter. It's not going to matter. You're going to come to me. You're going to say there's this constant k, and I believe that k-layered networks can approximate anything. You know, ResNet k, whatever, ResNet 50 is the ultimate thing. You never have to do anything else. And I come back to you and I say bad news. So I can construct a function with quadratically as many layers, and the only way your thing with k layers, so I'm going to have k squared layers, you're going to have k layers. The only way your function can approximate mine is if its width is 2 to the k. So let's just compare this to what we had earlier. What we had earlier was from 2 ReLU layers to 1 ReLU layer. There's an exponential, you need to blow up the width exponentially. Now I'm saying from k squared layers to k layers, you also might have to pay an exponential blow up in the width. Okay? So that's what this theorem says. So there exists a function f modeled by a quadratically sized and quadratic depth ReLU network. And this function f, you can guess what it is. It's just the k squared fold composition of these tent maps. Okay, it's the simplest you can get. So that if you give me any ReLU network that has less than or equal to k layers and less than or equal to 2k nodes, then it's a constant off. Okay, so a few remarks about this theorem. Let me just give a quick comment on the proof. So the proof works by a kind of an oscillation counting argument. This is actually the main novelty in the proof. So while it's intuitively true that if I have a function with few oscillations, you know, with few layers, and I try to compare it to a function with many oscillations, it's intuitively true that there's a gap between these two. You know, making the argument precise is another story, and that's the main novelty on this argument. The hard function f was just this k squared plus 3 composition of these these tent maps. And I should also say that another part of the proof is arguing that few layer networks have few oscillations. And people keep republishing this bound, the number of affine pieces in a ReLU network. It gets republished like every 3 years, I mean, at least. And I was trying to dig up the earliest reference, and I have a funny one, so just because of what city I'm in. So I mentioned Kolmogorov earlier. Another famous Soviet mathematician is Vladimir Arnold, and I found the magic trick to find all the Vladimir Arnold videos in YouTube a couple years back. I just write his name in Cyrillic and I put it in. So I went to a random Vladimir Arnold video I found in this way where he's talking Russian. I jumped to a random piece in the video, and he was actually counting these affine pieces. I don't know what this coincidence was, but so I gave him a question mark citation for this too. Okay, so if you look at the slides, the proof is there. I will skip it, but let me give a couple remarks on this theorem. So to summarize the 2 results I gave you and again, my purpose here was to justify why depth might help in this sort of approximation theoretic sense. So I gave 2 theorems. One was saying that if I have 2 ReLU layers, it can be hard to approximate with 1 ReLU layer. Namely, hard to approximate means I need exponential width. And then I also said that if there's some free parameter k controlling the number of layers, if you have k layers and I have k squared layers, you're going to need width 2 to the k. So those are 2 kind of results that say that we need we need a certain amount of depth, that depth helps. But then there are actually almost an infinite number of bad things about these results. So these results aren't, they aren't finishing the story in any sense. So one problem is that for this tent map construction, the Lipschitz constant is exponential. And if you just run PyTorch, you just do your PyTorch TensorFlow, whatever you want on CFAR, you're not going to be getting these kinds of Lipschitz constants. And in fact, if you try to train and fit these functions, unless you work very hard and do a lot of clever things, you're not going to be fitting these iterated tent maps. So these functions don't seem to be completely representative of, don't seem to be that relevant to what happens with gradient descent. That said, it is actually a little weird that it's been very hard for people to make improvements on this. So the natural thing everybody would want to prove is that just adding one layer is beneficial. And there's no one knows the answer to this question. And another question that's also very interesting is algorithmic. Let's say you have ResNet 50, and you would just really like to know if ResNet 51 would be any better. But the only recourse you have is, of course, just to add a layer and retrain. So yeah, there's also an algorithmic question here. Okay, any questions on this part? Linearly, it's fine.
So basically, you're saying that those increase something just because the number of parameters is less than 30% the same.
Yep. Yeah. So let me repeat the question and also add one more comment. So the question was, is it the case that it isn't actually that much worse because the number of parameters grows, let's say, linearly with the depth? So yeah, that's the way to think about it, that we still have very few trainable parameters, and kind of trainable parameters is kind of the real commodity that we're measuring the complexity of the problem with, and dictates the amount of time for the gradient steps and stuff like that. I will say that there was another big difference between these two theorems that I should have highlighted better, which is that for the first half, or all the first approximation results, we were saying given any continuous function, I can write it down with a shallow network. I certainly was not saying that for any continuous function, I can do better by using a deep network. I only gave you a couple very handcrafted special deep networks that are, special functions where deep networks help. And of course, the question that everybody would like to answer is, if you give me a natural function, or a function that appears, in nature, or gradient descent confined, or something like that, does depth help for these? So that's the question everybody would like to answer, and nobody's been able to answer. Yes. So the question is there any story with the activation functions? So for many of the theorems, you can convert between the activations, no problem. You just approximate one activation with the other, do univariate approximation, just plug the bound in and just pay off some constants. There are a couple theorems I only know how to prove really well with the ReLU. So the ReLU actually is, it's not just a proof thing, but the proofs hint to me that the ReLU is quite nice, but I'll just leave it at that. Tomorrow when I talk about optimization, the optimization results, there are really two activation functions they're like two families of activation functions that are good for optimization. One is the ReLU is very nice, and also smooth activations are very nice for very different reasons and very different regimes. Okay, any other questions? Okay, so let me sample a few remarks, a few different sections before we finish. So, sorry, I can't hear. Oh, yeah, we'll do this. So the question is that if we have depth, so far we've only done lower bounds with depth. Do we also have upper bounds with depth? Upper bounds that get better with depth. Is that your question? Yeah, that's actually the next section. That's what we'll talk about right now. Yeah. Okay, so one result I'll kind of sketch sort of briefly is this one I mentioned by Dmitry Urotsky sitting in the back here. So if your function has certain nice regularity properties, if it's very smooth, so in other words, there are a bunch of derivatives and they're all pretty small, then you can do a lot better with the deep network, so directly answering this question. So let me just explain this proof it's kind of a, it kind of relies on a sort of magical trick that I won't explain fully. There are many different ways to prove this, but so here's a very interesting thing. So the function x squared, so it turns out x squared can be very well approximated with a deep network. I don't know if this seems intuitive to anybody. It certainly wasn't intuitive to me the first time I heard it. But x squared can be miraculously well approximated with a deep network. So let me show you the construction. So here's how it works. So first, I'm just going to divide up the domain 0 to 1 dyadically. So I'm just going to look at 0, 1 half 1, then 0, 1 fourth, 1 half, 3 fourths 1, 0, 1 eighth, 2 eighths, etc. Okay, so I'm going to look at these sort of binary expansions of the interval 0, 1. And I'm going to form the secant approximation. So I'm just going to make, it's kind of hard to see here, but the first one is x squared, 0 to a half to 1, 2 pieces, and then x squared 0, 1 fourth, 1 half, 3 fourths 1. Okay, so it turns out that there are two nice properties. One, this approximation converges to x squared very fast. So these HKs approximate x squared very fast. And it turns out that HK can be approximated by a network with depth approximately k. Okay, so the proof is actually, there's a couple ways to see it, but one is pretty magical. If I look at h1 minus h2, okay, so again, h2 is, so h1 is with, just this piecewise affine interpolation at some scale, and then h2 is double the scale, h3 is double that scale, h4 is double that scale. So the difference between h1 and h2 is magical. It's just this. Okay, it's literally this. So where have we seen this before? Okay, I just told you about it. So it turns out the difference between these approximations, these piecewise affine approximations, is exactly this tent map. So what this says is that I can just take the kth approximation here and write it as just identity x minus a summation of a bunch of these things appropriately rescaled. If you're curious about proving this, you can check this by an induction, and there are a couple other ways to prove it too. But anyway, this is totally magical. So x squared can be approximated very efficiently just by adding a bunch of rescalings of this tent map I just told you about. Okay, so who cares about x squared? Well, what x squared gives us is x squared gives us multiplication. So there's this identity right here called the polarization identity. It's you can look it up. It's actually very kind of fundamental. It gives a way to convert between norms and inner products and stuff like that. So this polarization identity says, look, if you have squaring, then I also give you multiplication. So squaring gives us a multiplication primitive, and now we can use all those multiplication results from earlier. So let me double check the time. So the nice, so we get multiplication, and multiplication means we get polynomials. Okay, so this tells us that deep networks can efficiently approximate squaring, and therefore they can efficiently approximate multiplication. They can do polynomials. And kind of the biggest set of things that follow this sort of direct line of proof is this result by Dimitri over here. So it says that if you give me a function f, and in addition to what we said earlier, it now has a lot of really well-behaved derivatives. Then with log 1 over epsilon layers and something like 1 over epsilon times log 1 over epsilon, the d over r there depends on the smoothness, these number of derivatives and things like that. Basically, you should take this to say that if you have a very smooth function, then if you have depth log 1 over epsilon and width log 1 over epsilon times 1 over epsilon to raise to the power of something depending on the smoothness, then you're very close. Okay, so this is a big improvement on what we had earlier in the sense that it has a benefit of depth and it's more adapted to properties of the function. So this is an answer to that question you had. So let me make a couple comments about this. So the proof, why is the proof actually very intuitive? So earlier I told you how to do polynomials, and I told you how to do multiplication. And so all this is doing is local Taylor approximation. If all these derivatives are well behaved, the Taylor expansions are well behaved, so I just locally Taylor approximate the thing everywhere, and then just do a bunch of multiplications and it works out. Okay. And let me just check the time. So I will say that in some sense, this is actually, I would argue, with apologies to the author, this is still somewhat a shallow approximation theorem because the function f only determines some coefficients in the final layer of this construction. It doesn't affect the lower layers, which are this polynomial basis in some sense. Okay, I think I'll adjourn this section with that. If you look at the slides, there's a bunch of parallel work. Yeah, I'll just, and they're also lower bounds, and this is tight in some sense. So I'll stop that there. In the final time, let me just tell you a couple cute random things. So yeah, I just have a couple more minutes, and I don't want to eat up the break too much. So one quick comment was that Marco, in the optimal transport tutorials, there was one point, I don't know if everybody remembers, but there was a question about topology. When we're doing these transport mappings, there's this point where the thing has two pieces, then it has one piece. I don't know if everybody remembers this question. And what that effectively implied was that the transport mapping had an infinite Lipschitz constant there. So people use GANs. GANs are deep networks that you take a random sample from a distribution, pass it through the deep network, and you get a sample from another distribution. And you can ask a lot of these approximation theoretic questions for GANs. And you run into a lot of issues based on these Lipschitz constants. So if that interests you, you can look up this literature. Another okay, good. Another quick comment is that oftentimes I mentioned infinite width networks, and then I would very quickly talk about finite width networks, and I gave absolutely no explanation about how you did that. So there's actually a very clean, and there are two clean and trivial ways to go from an infinite width network to a finite width network. You do it just the same way we like going from infinite width to finite things all the time. We sample. We can view it as a distribution over nodes, and we just sample from it, and it actually works. And there are a bunch of ways to prove it, and I can tell you more later. Maybe I should close with the picture I started with. Oh, just another funny thing I can tell you. So recurrent neural networks, they can approximate Turing machines with no need for like a memory or a read ahead or any of this other stuff. Just a recurrent neural network. With one caveat, I need infinite precision real numbers. So these things can do Turing machines. The proof is simple. I take my Turing machine. It has a state transition table. It has a tape. I encode my tape as this real vector I pass. That's the state of the RNN from iteration to iteration, and like the cell of the RNN is the transition table of the Turing machine. So yeah, it can be Turing complete, no problem. So let me close then with this picture. So what's the story here? So I think I have the theorem here. So here's the crazy theorem at the bottom of the page. So this crazy theorem says, you give me a function g that's continuous. Can I write it as a very fancy two-layer network? Okay, sorry, two activation layer network. So what's going on here? So I have sum from 0 to 2d of fi. Fi are univariate. And then I have sum from j equals 1 to d of hij xj. So I take my input and I just slice it up univariately. I just take the different coordinate projections. I pass it through these functions h, sum them up, pass them through the functions f, and I claim that I get the function with equality. Okay, this is very different from everything I've told you today. All the other theorems had approximation. This thing only has quadratically many nodes. Okay, so does anyone think this is true? Right, so how is it different from what we did earlier? It has only quadratically many nodes in a dimension. It's unlike anything we talked about. And it has an equality instead of an epsilon close. There's no epsilon here. So is this true or not? So who wants to make a wager on what it is? Okay, so it's a Kolmogorov theorem, but here's the thing. You're just saying that because you knew that. But I would actually argue that it's very, very, very plausible to think it's not true, because this contradicted a Hilbert problem. So Hilbert, yeah. If you look into history, you can find out more about whether Hilbert was actually wrong or not. But let me just say, this is this Kolmogorov theorem. And hilariously, when I went to the grave on Sunday, I actually wrote it down on a piece of paper and took the picture. So that's the theorem there. So let me just tell you the theorem in more detail. So yes, there exist these feature mappings, hij, so that for any function you give me, I can find these outer layer functions. So I'm doing custom activation construction. And let me just say, this proof has a lot of mind-blowing pieces. I will just say two of the mind-blowing pieces in it. And this is from the 50s, by the way. Okay, this proof is kind of freakishly strong. There are two mind-blowing things in it. One, the functions hij, the way they work is they're space-filling curves. They're fractals. Okay, kind of mind-blowing. Two, the way it gets the equality instead of the approximation with the epsilon is it actually solves the problem at all possible scales and sums them up and then proves it converges. And the proof, it looks like a boosting proof. It looks literally just like the way you prove that boosting does things by adding little approximations on top of each other. So yeah, there are a lot of kind of amazing things in this proof. So I'm over time. Maybe I'll just take like one question and then we'll stop. Anyone wants to ask a question? One question? You're the last one. It's too late. It's almost like I planted this guy in the audience. You know, so I owe you like $100 for asking this question. This is like, how much do you want? I'll give you a credit card no, I mean, I really just, okay. So the question was that there was a random comment in the slide that says that the strongest, so, you know, you can make it work for ReLU, you can make it work for, the strongest version of the theorem is that the universal approximation works if and only if the activation is not a polynomial. And of course, people talk about using polynomial activations all the time. So the question is actually, the real answer is quite subtle because in real deep networks, the width is like blah, the depth is blah. So, you know, you can still get very many functions. So it doesn't have any practical relevance. But the mathematical version of the theorem is very clean. So if my activation is a degree R polynomial, and I add together a bunch of degree R polynomials, what do I get at the end? I get a degree R polynomial. If your activation is a degree R polynomial, your shallow network only gets degree R polynomials. You compose degree R polynomials, it only doubles. So using polynomial activations is busted. The more interesting part of the theorem is the reverse direction. The reverse direction that says that it is a sufficient condition for universal approximation if you are not a polynomial. You can use any weird thing you want as long as it's not a polynomial. You can use e to the x times x squared. And that proof, it actually, using the fact that you're not a polynomial, you have infinitely many derivatives. And so then you can use infinitely many derivatives to construct polynomials of any order. So it's this crazy theorem that says that if you are a polynomial, you're stuck in polynomial land. If you're not a polynomial, you can use Taylor's branch to get any polynomial you want. And now you can approximate anything. Anyway, with that very strange comment, I'll stop for the break. And tomorrow we'll do optimization and generalization.